My name is Dr. Chee, Chong Hian, and today we're going to take a quick journey into the field of quantum chemistry, where we're going to study the behavior of electrons, atoms, and molecules from a quantum mechanical perspective. Now, before we start, as we explore, do observe anything that piques your curiosity, and do take it down like keywords or any if there's questions, and try to think and imagine the possibilities in your head, and after that come up with certain questions after and you bring them to after the end of the webinar. Now, a brief motivation. Now, most of you students here are perhaps studying for your A-level physics or chemistry, uh, perhaps juggling many concepts and topics such as kinetics, molecular bonds, energy, and perhaps studying organic and inorganic chemistry. Now, I know some of this can be overwhelming and confusing. And so if you are struggling currently, my advice is to don't give up, have some faith in your teachers, and try to have more practice. Of course, some of you might already feel comfortable with chemistry. And so if perhaps even looking beyond the classroom, um, and take certain science projects that's offered by your school, your university, or perhaps even an A-star. And of those kind of students, very good. Keep it up, maintain your curiosity, and make sure to focus on the impacts and the learning outcomes of your research. But regardless on your your studies in your chemistry, right? Allow me to pose one question to you today, right? Have you ever wondered what started modern chemistry? Well, the short answer is that modern chemistry began from quantum mechanics. Now, at first glance, it may seem odd, right? After all, quantum mechanics sounds like physics. So why does it even matter to chemistry? Now, from the perspective of the physics, right, all chemical phenomena is the result of the behavior of electrons. Now, to see this, let's take a simple example of a combustion reaction of a glucose in the marshmallow. When you burn this, right, all the carbon, hydrogen, and oxygen atoms retain their atomic identities. That is, their in their nucleus, the protons and the neutrons remain at where they are. Instead, the electron shifts from one atom to the another, breaking and forming new chemical bonds, right? And glue them together to form new molecules. In other words, the electrons are the real star of the show, and therefore they are the objects of study in quantum chemistry. So today, our guiding question is, what is an electron and how do I properly quantum mechanically describe it? Now, the UNESCO, the United Nations Education, Scientific and Cultural Organization, have declared this year, 2025, to be the year of quantum, to celebrate the 100 years after the birth of quantum mechanics. Never mind the fact that it was first Max Planck who first quantized energy way back in 1901 to solve the problem of the black body radiation. And his ad hoc solution has inspired or even garnered attention from many leading physicists and mathematicians of the time and fueled intense debates on the quantum nature of electrons and photons, such as the Solvay Conference in Belgium in 1927. Now, of course, I actually turned this into a Studio GB style image using a ChatGPT, a technology that could not be imagined by any of these people. It is a result of 100 years of progress in computer science and artificial intelligence. But despite 100 years of progress in physics, we are still nowhere near satisfying the conclusion of quantum theory, where all physicists and by extension physics teachers have no universal consensus on what quantum theory is about. And as a result, many people misunderstood quantum to be something that is extremely complicated or complex, that so much so that in everyday popular culture, the word quantum has been mislabeled as something mysterious or even downright futuristic. Now, I know that sometimes uh, quantum mechanics can be abstract, right, and confusing, and even physicists like me can find some aspects of quantum puzzling. And teaching it to newcomers has always been a challenge because certain basic quantum concepts of physics are just hard to picture in your head. And what made it worse is that some physicists like to introduce this subject with confounding paradoxes with no neat conclusions that could even alienate the most eager students. So for today, you are lucky because I decided on a show and tell approach, and I put together a special deck of slides just to demonstrate the quantum ideas that allows us to apply this to chemistry. And this is not something new. After all, chemistry is the first application of quantum mechanics and is done by Wolfgang Pauli in 1926, where he used it to solve for the hydrogen spectrum. Now, for today's webinar, we're going to take you to a learning journey where I will be introducing what is the key quantum idea that will help us to describe the electron proper and understand its behavior in certain scenarios, such as when you add a proton to the electron to form the hydrogen atom. Next, we're going to look at a special property of the electron called electron spin. And spin is a crucial in chemistry because it underpins many things, many chemical phenomena. For example, in a situation where one electron meets another electron of the same spin. Now, all of this will tie in to the last section where I will look into the bigger atoms and molecules from a quantum mechanical perspective. And I hope that you come out with understand that quantum is a powerful tool for chemistry. Now let's begin with the quantum idea, which is an abstract theory, not just for physicists, but I believe it should be communicated to the students and the public because it's such a powerful tool that helps us to describe our nature. Now, let us start with something concrete, a simple hands-on example known as the cathode rays. Let us take a vacuum tube and you put a metal cathode at one end and an anode at the other end. And you apply a potential difference about 10 to 20 kilovolts, right? And you switch on the current. Now, what happens is that the electron gets pulled away from the cathode and directed towards the anode, forming an electron beam called cathode rays. Now, the cathode rays itself is invisible. So to make it visible to your eyes, you have to let it strike a perforated card that is coated with a fluorescent substance so that you can actually see it. And if you have a magnet, you can actually deflect the electron beam, and this will demonstrate the Lorentz force in action that you have learned, or perhaps will learn in your physics lessons. And this simple demonstration will be our gateway to understand quantum mechanics. Now, the fun bit comes when you want to slide, when you slide a double slit into the path of the electrons. And what happens is that the double slit pattern will appear on the screen that's exactly identical to double slit experiment using laser light that you have learned in your physics class. And this demonstrates the wave properties of the electron. Now, if you were to turn down the current such that the electrons leave the cathode one at a time and lands on the screen one by one that is independent from the previous to the next electron, what you observe is a statistical pattern appearing on the screen whereby the concentration of the dots, right, reflects the same identical interference pattern, double slit pattern that you saw in the previous slide. And this concentration plot can be reinterpreted as a probability distribution of where the electron might land next. And this is the evidence that electrons have both wave-like and particle-like properties. And this is the essence of the wave-particle duality that you have done in physics. Now, of course, some of you may think that, well, this is nothing short of interesting. After all, the double slit experiment is a required part of your syllabus, and you're required to practice, memorize these basic concepts, and prepare for the questions that to be asked in your exams. Now, one may easily fall into the trap that thinking that this result is nothing but simple statistics. Well, let me point out to you that this is far from everyday normal notion of statistics. For example, if you want to obtain the combined distribution of two populations, well, what you do is to simply add up the two separate distributions of both populations. For example, let's say if you want to get the height distribution of the students in a class that's made up of boys and girls, what you do is just to add up the height distribution for boys and then the height distribution for girls. And that's how you get the combined height distribution. And if you apply this or extend this to the double-slit experiment, you should think that the statistics from the double-slit should be equal or matches the sum of the two statistics from each slit. Well, it turns out that this is simply wrong. The double-slit fringes will never appear in the sum of the two statistics from each slit. So how do we resolve this incompatibility? What is a solution that will be compatible with the observation that the electron is both wave-like, particle-like, and also compatible with our daily notion of statistics? Well, physicists have came up with a quantum idea, a new mathematical tool called the wave function. Technically, it's actually a vector, but actually you can picture it as a wavy way of tracking the position and the momentum of the electron. So now in this double-slit experiment, the position of the electron is now represented as a wave function, and is being directed towards the double-slit where it can create two separate wave functions, which will then interfere constructively and destructively, like how classical waves would. But in order to get back the interference pattern or the statistical pattern that we saw before, we will have to use a new rule, right? A rule that is called Bond's rule that tells us the probability distribution can be obtained by performing an absolute square on the wave function. That is to say that if you were to take a number from the probability from the wave function at a point, and you perform an absolute square on it, that number will be the chance of obtaining the electron at that point, right? And this result or this postulate is formulated by Max Born, who won a Nobel Prize for this statistical interpretation of the wave function. So going back to the double-slit experiment, right? The statistical pattern is just simply the sum of the two wave function, and in physics we call this superposition. And to get back the probabilities, we just simply do a modulus square on it. And this is obviously different from this sum of these two probabilities. So I know you have been bored by looking at from the interaction, you're bored by looking at static pictures of a wave function. So you might feel that the wave function still feel mysterious, complicated, complex, right? So let me help you by giving you the simplest example of a wave function using what is called a qubit, which is a two-level quantum system. Well, in real life examples of a qubit is as simple as atomic energy levels, right, that you have learned in chemistry, where the ground state and the excited state can serve as a 0 and 1 state of the qubit. Now, another simple example will be light, right, whereby the photon polarization, horizontal and vertical, can also serve as a 0 and 1 state of the qubit. Now, the wave function of the qubit can be just simply written down as a superposition of these two states, where the corresponding numbers, which we call the amplitudes in physics, can be, you apply the Bond's rule to get the probabilities, where this will be the chance of finding the qubit in either of these two states. Now, I'd like to generalize this by considering more quantum states. And I arrange them in a vertical axis here. And this system, right, will be a one-dimensional quantum object. And the wave function can be simply written down as a superposition of all of these states using a summation sign, right, which is denoted by this sigma over here, which stands for a shorthand for summing at all the quantum states out. Right. Now, I would like to take a further generalization, right? Why stop at 1D when we can go into 3D? Now, every quantum state here is being represented by a cubic lattice point here. And this is a three-dimensional quantum object where its wave function can be written down identically like the 1D case, where it's just a triple sum, the superposition of all of these states here. Now, I'd like to take one final leap of generalization where we consider that every point in space is a quantum state. And then you take the superposition of all of these states here, and that wave function will be the wave function of the electron. Now, here I have to use an integral because we are summing over continuous space, so we cannot use the discrete summation as before. And the electron can now be interpreted as a three-dimensional quantum object. But usually for pedagogical purposes, we simplify down this to 1D or 2D dimensions. And I would like to emphasize is that the electron wave function is not the electron, but rather is a representation of the electron's position or the momentum. And this wave function is such a useful theory that that Richard Feynman, a famous physicist, once called it almost real. So I believe most of you have been bored by looking at pictures of static pictures of wave functions, and I know that you're looking for action, right? So let us look at some simulations, all right? Let's consider the one-dimensional free electron, where the electron feels no obstruction at all, and we just let it move across space. And I initialize the wave function to be like a sound ripple in space, but when you look at its probability distribution, it looks like a bell curve that somehow all students like to worship for your exam grades. Now, let us see the simulation. Now you observe two things. As the electron moves across from the left to the right, you observe that the wave function actually widens and flattens. The reason why it flattens is because the electron has a superposition of multiple momentum states, meaning that it has multiple velocities. And this is due to the fact that the Heisenberg uncertainty principle, which states that there is a limit to how much precision you can measure the position and the momentum of the electron. Now, the second thing that the wave function is flattening is because it's trying to compensate for the widening of the wave function, because the area under the curve of the probability has to remain at 1, since it represents a total probability of finding the electron at all space. Now, I can further generalize this to the two-dimensional case, where the left-hand side represents a wave function, and then when you do a modular square, it gives you the probability in this case. And from here, I believe most of you, right, can imagine what a three-dimensional electron will look like, right? So imagine that the wave function will be like ripples in space, and then when you turn that into a probability in distribution, it will look like a soft spherical fuzzy cloud that is drifting through space. And that is the picture of the free electron, right? Now let's go back to the one-dimensional case again, and I try to make it interesting by letting it strike an energy barrier, where inside the energy barrier, the electron will feel a repulsive push, right? Now, I have to split this into three separate cases: low, just about right speed, and then high speed. Low speed means that the kinetic energy is much, much lower than the energy barrier. So let us see what happens. Well, as the electron approaches, right, you see there's a fine set of fringes. The reason why we see fringes here is because the incoming electron wave function is interfering with the reflected wave function, right? So that's why you see the fringes here. Now, how about when it's just about the right speed, meaning that the kinetic energy of the electron matches the potential energy barrier? Now, what happens here is that part of the electron gets transmitted and another part gets reflected. And this phenomenon is called quantum tunneling. Now, to be clear, there is only one electron here. So what this means is that there's 50-50%, roughly 50-50% chance of finding the electron at both sides of the barrier. Now, for completeness sake, let us look at what is when it's at high speed, when the kinetic energy is much, much greater than the potential barrier. And I think that you should know how it will behave. Well, most of it just gets passed through the energy barrier, leaving little reflected back, right? Now let's look at the double slit experiment again with the simulation, right? And I let it strike the infinite barrier, means there is zero chance of quantum tunneling, but with two slits. And look carefully, like what is the difference here in this case? Now, obviously, there is this double slit pattern that we saw before, but now, in addition, there is this self-interference pattern that wasn't observed before, right? So this is something new. Now we come to the end of the first section where I've discussed or introduced the quantum idea of the wave function that helps us to describe the electron as a three-dimensional quantum object that is useful for calculating the chance of finding the electron at a position. Now you may notice I've added a asterisk beside the word object, and that's because it is not the full picture. Right? In fact, the electron contains another special property that is not discussed that will be discussed at the later part of the webinar. Now, of course, you can actually run other kinds of simulations, right? For example, putting an electron in a bowl, and you'll just look something like this, where the electron wave function will just bounce around, and you can actually scatter the electron apart using a circle in this case. So in this simulation, the electrons seems to get obliterated, but when you try to measure, it will appear somewhere in the space. Now, let us move on, right, to the next section where we try to add a proton to the electron to form what is known a hydrogen atom. And as a result, the probability cloud looks something like this. Now, what you're observing is the first direct observation of the hydrogen atom, where the darker red and yellow parts represents the areas where the electron is most likely to be found, and the darker blue areas represents the areas where the electron rarely visits. Now, because we cannot directly observe the wave function, so we have to settle for the probability cloud. And this probability cloud is known as the atomic orbitals that you have learned in chemistry. And in this particular case is the ground state of the atom. Now, just to be clear, in physics, the atomic orbitals actually represents two things: either the electron wave function or the electron probability cloud. So sometimes I know it can be confusing, so always check the context. So in this case, I'm talking about the probability distribution. Now, as you pump energy into the hydrogen atom and you make the atom excited, what you observe is that the atomic orbitals, they get bigger with more gaps appearing in the orbital that's represented by the darker patches in the probability cloud. And these gaps, they are called the orbital nodes. And you might be wondering, why are they orbital nodes here? But before we get into that question, let us take a short uh, diversion to understand what do we mean by atomic orbitals. Well, atomic orbitals are just simply electronic wave function or probability cloud when the atom is in a stationary state, meaning that the total energy of the electron remains fixed throughout time, and as a result, its probability cloud remains fixed as well. And this has analog to the standing waves they are learned in classical mechanics, as shown in this animation or video of a water wave oscillating up and down, but not traversing across the water tank. And in the case of the atom that is in a stationary state, the wave function may oscillate up and down with its phases changing, but its resulting probability distribution remains fixed in space. Now, if we were to superpose this stationary state, right, it will no longer become stationary because the resulting probability cloud will oscillate in time, and this will cause the energy to oscillate between these two energy values. Now, for the energy that's associated with the atomic orbitals, they are called the orbital energy. And they are exactly the same energies that you have learned in the atomic energy spectrum, where the electron transition between any two of the uh, atomic levels correspond to the emission of the photon when the electron is de-excited, or absorption of photon when the electron is being excited. Now, this example shows the hydrogen emission spectrum. When you let the excited hydrogen atoms cool and allow it to release energy as radiation, you will emit visible light at 5 Pacific frequencies that is known as the Balmer series. Right. Of course, there will be other frequencies released as well, like the infrared and the ultraviolet. So for students that have been paying attention, let me give you some food for thought. When you carry out this experiment, do you think that you should wear protection glasses? Now, if you do know the answer, please let us know at the end of this webinar where we have time for discussion. So let us move on. Now, let's go back earlier question where we ask why are there orbital nodes in the atomic orbitals? Well, let us consider the first a simpler example. Let us suppose that the wave function looks something like a sine wave. You notice that the sine wave, they cuts the x-axis at multiple spots, right? And when you use the Bond's rule, right, to get the probability, all of the values becomes positive except for the points where the curve touches the x-axis as they remain at 0. These points are called the nodes. Now, to see how is it applied to the atomic orbital, consider the radial wave function or the radial part of the electronic wave function of the atom. In the ground state, it looks something like this, right? The wave function starts off with a positive y-intercept, and then it exponentially decays as it moves away from the center of the atom, which is at the proton, right? And then when you apply the Bond's rule to calculate the radial probability, right, what you observe is that there is no nodes, right, except the point where the proton is, which is kind of obvious because the electron will never be at the proton itself, right? And some of you might wonder, why is there an R square over here? Well, when we want to calculate the probability, we are calculating over the spherical surface, right, of the atom. That's why the R square is to account for the area of the sphere. Well, strictly speaking, there should be a 4 pi over here, but that could be absorbed into the plot. Now let's look at the first excited state. The radial wave function looks something like this. And you notice there is a single x-intercept, and that is where the node is. And when you look at the radial probability, there is the node appearing. And this is why you saw the gaps appearing in the atomic orbital. So in general, has the atomic, has the atoms get excited, right? The atomic orbitals, they become bigger and that contains more and more nodes. Now, for those eager students out there, right, let me pose another question to you. Why do you think that as the atom get excited, why do you think that the orbitals become bigger? So if you do know the answer, well, please do share it with us at the end of the discussion. Now, what we have been looking at or discussing are just the spherical shape with the probability cloud that is called the s orbitals. But there are other kinds of atomic orbitals that has a higher energy than the s orbitals. They are the p orbitals, which looks like a dumbbell shape, right? There are the d orbitals, which are looks like a clover leaf, and then there is the f orbitals, which are much more intricate. Now, one final food for thought for your guys who has been paying much attention to this lecture is that why do you think that we actually stop at f orbitals when there could be more, right? Now, let us move on, right? If you want to visualize the atomic orbitals, Minute Physics has provided an awesome visualization of how the atomic orbitals will look like. Now, take note that the dots do not represent the electron, but rather the concentration of points represents the probability that you're going to find the electron there. Okay? Looks cool, right? Now, let us move on. In summary, what we have discussed is that the atomic orbitals are just simply the electronic wave function or probability cloud of a stationary atom, meaning that its energy does not change over time. Okay, so this is the summary of the section, the atom section. Now let us go to the next topic on the electron spin. Now, the electron possesses a unique quantum property called the electron spin. And when I say spin, I do not mean that the electron is literally rotating at its own axis, like a spinning top. But rather, spin is something that allows neutral atoms to deflect in a magnetic field that is similar to a bar magnet. Now let us see what is this deflection using what is known as a Stern-Gerlach experiment. Now, this experiment consists of the following. First, it consists of an oven that generates hot vapor beam of silver atoms that will be directed towards a non-uniform magnetic field that is perpendicular to the direction of the beam, and then you hits a detection plate that we will see a pattern. Now, the reason why we use silver atoms is because if you look into its electronic structure, you'll observe that there is a single electron at its most outer shell, while all the rest of the electrons are all paired up in its inner shells. And this gives the atom a resulting net spin that will interact with the magnetic field. Now, let us suppose that the silver atoms behave like simple bar magnets. And what you expect on the screen is a continuous spread of silver atoms, right? Just like bar magnets. And this is because the oven will probably generate silver atoms where its magnetic dipole will point uniformly in all directions. And since the vertical magnetic field will deflect the silver atoms vertically, you will expect that the deflection will be uniform in the vertical direction. But this is not what happens. In fact, the silver atoms will be deflected up or down, but never in between, right? And this demonstrates the existence of the quantum spin, a special property that gives silver atoms this behavior. Now, in actual results, right, it looks something like this. When you have no magnetic field, it just simply looks like a horizontal line without a vertical deflection. But when you turn on a non-uniform magnetic field that is pointing upwards, right, there is this deflection here, right? So the silver atoms is either deflected up or deflected down, but never in the center. And this is contrary to the classical results if you were to assume that the silver atoms acted like tiny bar magnets. Now, what is the significance of electron spin, right? What's the point? Well, electron spin is the source of magnetism. And in fact, magnetism is actually a quantum effect. And to see this, let us take a step-by-step approach. Let us first look at the iron bar magnet, right? Simple, in the magnetic field. And the bar magnet contains many iron atoms that contain many unpaired electrons in its 3D shell, and this gives the magnet a strong magnetic dipole. Now, when you isolate the many atoms, right, that contains at least one unpaired electron, you will notice, and you put it through a magnetic field, you will notice that it will either deflect up or down. And in this case, right, when the silver atoms, right, has a spin that is pointing downwards, its magnetic dipole is actually pointing upwards in this case. And this is aligned with the magnetic field, and therefore we can label this as a low energy state of the atom. In this case, the silver atoms will be deflected upwards, right, because it's attracted to the magnet upwards. And in this case, when the spin, right, is pointing upwards, right, the magnetic dipole will be pointing downwards, right? It means that it has high energy, right? And then we can label this as one state, right? And this seems like it behaves like exactly like a qubit. Now, if you were to isolate this further, that causes the deflection, you'll realize that the electron spin behaves just exactly like a qubit, right, with two levels, right? And if you combine this with the atomic orbitals using what is known as a Kronecker product that combines two different kinds of quantum state, you obtain a legit wave function or a quantum state of the electron. But this is not the full electron because there are many possible states as well. Therefore, to get the complete description or the full wave function, you will have to superpose all possible combinations of the orbitals and the spin states. And this is the full electronic wave function in an atom. Now, so in summary, right, we have learned that the electron spin behaves exactly like a qubit, and when you put a bunch of them together, it becomes like a tiny magnet, and this is where magnetism comes from. And we have also learned that the electron is just simply a three-dimensional object plus a spin component. Now, let us talk about what happens when one electron meets another electron. Now, in classical physics, this is just pure, simple electrostatics, right? It's just two negatively charged particles repelled each other by Coulombic forces that is pointing opposite away from the center of separation, whose the magnitude is inversely proportional to the squared separation distance. Now, this is to be fair, I mean, to be real, it's quite a boring system. But we have learned moments ago that electrons can be described using the wave function. So, and this presents an interesting case. What happens when one electron, or when electron wave functions interfere with each other? And the second question, if they actually interfere, how do I tell them apart? Now, the starting point to approach this question is to ask ourselves, how do we distinguish between objects? Well, for example, let us give you a picture of some balls, and I ask you the question, how do I differentiate these balls, right? You can tell me that I can differentiate the balls by looking at this color, its pattern, its texture. You can also weigh the ball and tell me that one ball is heavier than the other. Regardless of what, right, you can actually distinguish based on its physical attributes, right? And that is important. But what happens when I ask you to distinguish between identical objects, meaning that they have the same physical attributes? Now, when I say identical, what I meant is that, as a saying goes, if it looks like a duck, it swims like a duck, it quacks like a duck, is probably a duck. So in this case, you would probably say, okay, I can distinguish them by marking each and every object with a marker. You put a sticker on it, something like that. Now let us suppose that we can't do it, because doing so will change the physical attributes of the object. Now, what other ideas do we have? Well, we can also distinguish the objects based on their position and the momentum, right? So for example, in a simulation of gas particles, they all look the same, but they have different position and momentum, such that I can tell apart between a fast uh, particle and a slow-moving particle. As long as I keep them inside, I'm able to distinguish them. Now, what happens if I want to distinguish two electrons of the same spin? Now, to be clear, if the electrons have a different spin, then obviously there are different physical attributes and I can distinguish them. So in this case, I'm going to talk about when two electrons are of the same spin. Now, all of the electrons in the universe have the same mass and charge. So distinguishing them based on these two properties will not be good. So how about distinguishing them based on the position and momentum that we have just established? Well, let us make it simpler. Let us just suppose that both electrons have equal speed, and we want to distinguish them based on the positions of the electron. And I split this into two sub cases. Let us suppose that they have low speed, and I set it to approach each other uh, and meet at a specific point. And I plot the probability distribution of finding any electron. As you can see here, because of the low speed, the Coulombic force is overwhelming to such that they have little chance of overlapping. And in this case, it is distinguishable. You can actually track the positions of the electron. But what happens when both electrons have such a high speed that it overwhelms the Coulombic repulsion? Now, what you see here is that the two electrons interferes with each other so thoroughly that you have no idea which electron went to which direction. Did the electron quantum tunnel through each other, or did they actually collide and deflected away from each other? You have no idea. And this brings us to the concept of indistinguishability of identical quantum particles. Is when it happens when you cannot distinguish them. And it means that when you swap any of these two particles, you do not change the probability distribution, right? Means that they are identical, right? And as a result, if you were to use the Bond's rule and you want to find out what is the wave function, you find that the wave function must satisfy the following condition, is that the swap wave function must either be identical to the initial wave function or it picks up a minus sign. Now, a bit of terminology here is that whenever the wave function picks up a positive sign, it means that we call the wave function symmetric. And when it picks up a minus sign, we call this anti-symmetric. Now, example particles that has a symmetric wave function is photon light. So what this means is that when you swap any two photons, the wave function is just identical, is the same, right? But for those particles that are antisymmetric, examples are electrons and photons, meaning that when you swap any electron, the wave function will pick up a minus sign, right? So it will not be the same as before, but rather it will be a negative of the previous wave function whenever you swap any pair of electrons. And this has strong implications on how they actually cluster together, the effects on particle clustering. So here I want to plot the probability distribution of finding one particle on the bottom axis, and then the other position, second particle at the vertical axis. Let us look at the photons first. When you plot the probability distribution, it looks something like this, right? That it clusters along the diagonal, meaning that the photons like to be close, or being at the same position where the two photons at, right? Means they like to be near with each other. Now, what about for the electrons with the same spin? When you plot the probability distribution, you realize that they avoid the diagonal, and this means that the electron don't like to share the same space with each other, right? And this effect, right, is called the Pauli exclusion principle. It means that no electrons can actually occupy the same quantum state simultaneously. And this has nothing to do with the Coulombic repulsion forces, right? It's a purely quantum effect. And this is the same reason why you are not allowed to pair the spins with the spins aligned, right? When you fill up the energy levels diagram. When you do that, it means that they have the same quantum state. And Pauli exclusion principle explicitly deny this. Therefore, you're only allowed to anti-align the spins because this will mean that they have different quantum states. Now, that's it for the two electron section. We have just learned that the electrons do not cluster when they interfere in the same state, and this is called the Pauli exclusion principle, which underpins many quantum chemical phenomena that you'll learn in your chemistry lessons. It is also the same reason why objects are so big and bulky, and that is because electrons do not like to share the same state, position state with each other. Now, for the photons, you might be wondering, right? They like to cluster if they interfere, and that effect is called the Hongo-Mendel effect, which is something that I don't think you have ever learned in physics. So it is it has interesting applications in, let's say, photonics or communications. And please do check it out in your own free time. Now let's move on to the next section where we're going to talk about bigger atoms. Now, earlier in the webinar, when we are in the hydrogen atom case, we discussed that the atomic orbitals are just simply the electronic wave function or probability cloud when the atom is in the stationary state. And you might wonder whether can we do the same for bigger atoms, right? Like, for example, sodium atoms that contains, say, 11 electrons. Can we do the same thing, find out what is the atomic orbital? Well, unfortunately, solving for a stationary wave function that contains two or more electrons is extremely complicated. So much so that solving the stationary state of the helium atom that only contains two electrons is impossible to do it analytically, let alone a sodium atom. So what do we do in this case? Well, quantum chemists came up with, they had to rely on approximations and rules to find out what is the wave function. An approach that many of you have undertaken before is to suppose that each electron occupies an atomic orbital with a definite spin, and you use it to fill up the energy level diagram. Well, the field energy level diagram that has the occupied spins, they symbolically represent the ground state wave function of the atom. In other words, you're actually drawing a representation of the electronic wave function. Now, of course, the Pauli exclusion principle by itself is not sufficient to fill up the energy levels. Therefore, you need rules to do so. And these are all distilled by decades of chemical intuition. Now, examples of this includes like the all-above principle, where you, to write down the ground state, you have to fill the energy levels in the specific order, 1s, 2s, 2p, and so on. The other one will be the Hun's rule, right, which means that you have to fill the subshells singly before you pair them up. And this has to do with the observation that things are magnetic, right? Paramagnetic, diamagnetic, so on and so forth. Now, all these approximations and rules, they actually work very well, actually so well, in fact, that you can actually use it to organize and arrange the elements in this ground state based on its outermost shell occupied, leading to the periodic table arrangement that you all come to love in your chemistry lessons. So that's it for the bigger atoms. Now I want to talk about molecules where two or more atoms come together and form molecules. And an example I want to talk about is the simplest case, right, which is the hydrogen molecule, where you have two hydrogen atoms form together to have a covalent bond in this case. And this covalent bond can be described using the concept of molecular orbitals, which has a crazy technical definition in quantum chemistry and is called the linear combination of atomic orbitals. You will see this popping up almost everywhere in your chemistry textbook. But from a quantum perspective, it just simply means the quantum superposition of atomic orbitals, whereby in this specific case, you take the 1s orbitals from both atoms and then you superpose together to form two possible molecular orbitals. And this bottom, called the bonding and anti-bonding or molecular orbitals. And if you were to apply the same approximation and the rules as before in your bigger atom case, you can actually obtain you actually approximate the wave function by just filling up the molecular energy levels. And in this specific case, it actually corresponds to the bonding orbital, which makes intuitive sense. And if you were to plot the orbital's energy, right, for various bond separation and draw its the bond molecular shape, what you get is something like this, right? So over here is the orbital shapes at various bond distances, and these are the various bond energy, where the bottom curve and upper curve represents a bonding and anti-bonding orbital energy. And this curve is known as the molecular dissociation curve. Now, what is interesting here is that there is this minimum, a dip in the bonding curve at 0.074 nanometers. And this tells us that this molecule is likely to be stable at this point because the minimum is actually much lower than the case when the atoms are far apart because it has a higher energy. Now, I'd like to say that these are not the only two molecular orbitals. In fact, there are actually more molecular orbitals. And for the next simulation, you shall see all the various molecular orbitals possible. So this one is the bonding orbital, right? And then this one is the anti-bonding orbital. And the next shows all the higher possible molecular orbitals, right? So in the actual description of the molecular bond, it actually contains a superposition of all of these molecular orbitals that you're seeing here. It just so happens that when it's in the ground state, it likes to occupy the bottom molecular orbitals. So there are many intricate shapes and sizes that the two electrons can occupy. So if you understand the molecular bonds via the molecular orbitals, you can probably extend this to understand or visualize how chemical reactions will progress in this case by looking at how the electron wave function transforms as the reaction progress. So on the left represents the electron transfer. So and on the right represents a hydrogen atom transfer, and you can see how the electron wave function will behave in this case. And this has leads to a strong study in how the properties of the molecule. So in summary, right, we have learned that the atomic and molecular orbitals, right, and they can be used to help us to approximate the multi-electronic wave function, where you assume that you suppose that the electron is occupying these orbitals and you fill the energy levels. And that is a representation of the multi-electron wave function. And for the molecular bonding, can be described using the concept of the molecular orbitals, right? Has a superposition of the atomic orbitals. And here is a simulation of how the bonding of the oxygen molecule with its 2s and 2p atomic orbitals. Okay. Now, so we come to the conclusion of the webinar, where we have saw quantum mechanics have explained almost all the chemistry and most of physics as Paul Dirac states or asserted. And throughout this quantum journey, you have learned that this quantum idea of wave function can be abstract, but it's also instrumental in how we describe nature and also the behavior of the electrons in various scenarios, like quantum tunneling through an energy barrier, or forming the hydrogen atom to form the atomic orbitals. And with two or more atoms coming together to form a molecular bond, we can understand describe these molecular bonds using the concept of molecular orbitals. So if you'd like to know more about quantum chemistry, I provided several resources here. The liberal text chemistry is excellent for beginners who are fresh. I mean, they have no idea of what quantum chemistry is about, and this will help you guide through step by step on what is chemistry all about. Now, for those who are quite physics inclined, I suggest hyperphysics, and you'll introduce this subject from a physicist perspective. And yeah, if you are those who are extremely ambitious and want to go above and beyond, I would recommend all these 4 textbooks, which will give you a solid foundation in quantum chemistry in university. Now, a bit of background from where I came from. I graduated from the Center of Quantum Technologies, which is Singapore's flagship national research center that's established way back in 2007 and is mandated to perform research on quantum mechanics in applications such as quantum communications, quantum computing, quantum metrology, and so on and so forth. And please do check out their website. It offers many opportunities for you young students to perform research there. And myself, I did my doctoral work where I programmed quantum computers to perform basic certain chemical calculations, such as estimating the energy of a molecular bond. So we have come to the end of this webinar, right? Thank you for listening to my lecture. And please do stay tuned for the discussion time to talk or discuss about the food for thought or the questions that I've introduced in earlier in the webinar.